This video will be a factor scores demonstration using simplest case data from section 4.4 in your textbook. Factor scores are estimates of the underlying scores on the latent variables for each observation. Since the factor scores are created in standardized score form, the original data must also be converted to standardized form for the calculating of factor scores. The Z matrix can be created from the original data by post-multiplying the matrix of deviation scores X, as shown in this equation, by a standardizing matrix E, that is a diagonal matrix of reciprocals of standard deviations. It'd be easier to see what I'm talking about if we go back to the Excel spreadsheet that we used for video 4.8, in which I already have deviation scores. So if we go to step 1, we'll see I have deviation scores right here that I calculated from the raw data and the means of that data. So going back, I'm just going to punch it in here. We have the values 3, 2, 1, 1, 0, 5, 0, negative 6, negative 6, 0, 0, 0, negative 1, 6, 5, and on the last row we have negative 3, negative 2, and negative 5. Okay. Also going back, we have E here. Where E comes from is a diagonal matrix of reciprocals of standard deviations. Well, after we got our deviations here, we found the centered sum of squares and cross products matrix. And then we found our covariance matrix. Now remember, on a covariance matrix, the diagonals are variances, and the square root of a variance is the standard deviation. So we calculated these values by getting the standard deviation of those. So I'm just going to copy that, or excuse me, get the square root of the variance to get the standard deviation. So I'm going to copy that, and I'm going to paste it here. But I want to emphasize that this is going to be equal 1 over the square root of 4, which was the variance for the first variable. And then this one is actually equal to 1 over the square root of 16, I believe it was. And let's bring this out another decimal point. And then this was 1 over the square root of 22.4, which is the variance for the third variable. Now let's create the Z matrix to have this in standardized form. So do matrix multiplication of the deviation scores and a standardizing matrix, E, and we get these values. Our Z matrix here, the values are the manifest variable scores. Now the matrix of factor scores Y, which we're going to do next, may now be calculated by equation, the equation Y equals Z times T as the matrix product of the Z matrix and the T matrix. The entries in the Y matrix are the latent variable scores, and the entries in the Z matrix are the manifest variable scores within the two-factor space. So what I'm going to do here is, because I did matrix multiplication for Z, I can't just copy and paste that, so I'm just going to do matrix multiplication again here to get the values. And for T, we actually did this in the last video, video 4.9. I'm just going to copy those values and paste it in here. And remember, T is just a transformation matrix. So let's calculate Y through matrix multiplication. Z times T. And those are the values that we get for Y, which are latent variable scores, or also known as our factor scores. So once again, Z are manifest variable scores, and Y scores are the latent variable scores. And the T eigenvectors are actually the coefficients for transforming the manifest variable scores into latent variable scores. So like I said, it's a transformation matrix, and it's these are the coefficients needed to transform from manifest to latent variable scores. The latent variable scores y are also in z-score form, with means of 0 and standard deviation of 1. So if we go back to basic statistics, when we talked about z-scores, the mean is 0 and standard deviations are 1. Now moving on, matrix F can be used as linear combination weights to go the other direction, to transform the latent variable scores back into manifest variable scores. So basically from y back to z. And we'll use this formula, z equals y times the transpose of f. And remember that F is the matrix of factor loadings. So let's go ahead and do that. Y equals, as we showed here, z times t. So we get the same values. And then F, we can go back to our last video, or we can go back to our factor loadings, which I'll do in video 4.8. Take our factor loadings from the summary table here. I'm going to copy them, Control C, and then I will do a transpose paste. And let's multiply these two matrices together. And there you go. So let's look at the reconstructed z-scores in the z matrix that we just did here from the calculation. And if you notice, the values don't quite come out right. They're not the same as the z that we calculated up here. They're similar, like we have 1.4 and up here is 1.5, but they're not exactly the same. This is because the two factors extracted have not accounted for all the variance in the original variables. Now if we go back to the factor analysis summary table that we did in video 4.8, and I just went to get these factor loadings, this factor analysis only counts for 95.3% of the variance in the original data. So the factor scores are therefore only approximate. So once again, the reason why, let's go back here, the reason why that these z's are not exact, the two factor, is because the two factors extracted haven't accounted for all of the variance. So you noticed we do have two factors, and they only count for 95.3% of the variance. So that's just a demonstration of factor scores, or latent variable scores here.